Okay, welcome back, and let's continue the discussion on the scaling of the Burger equations and all this. So, we were looking at the kinetic energy budget. So, how we can get the kinetic energy equation? So, we have the Burger equation and we can multiply that with u and we get an equation in this form del t by u square by 2 plus u by del x nu del 2 u square by 2 by del x 2 minus nu del u by del x square. So, this is a term which an extra term which comes because of the multiplication of that velocity factor u, and this is known as dissipation, and you can define that by an epsilon. So, that means how we got it, that Burger's equation multiplied with u, we get this energy budget equation, or rather kinetic energy equation. So, this is my kinetic energy equation. Now, mean viscous dissipation we can also compute. So, the mean viscous dissipation we can compute from the exact solution by taking a limit where Reynolds number tends to infinity 1 by 2 L where epsilon dx, which will essentially you get this. And if you look at it, that means the dissipation scales with the macro structure and is independent of viscosity. So, this is another term we now come across, that so far we are looking at the kinetic energy. So, we can visualize this macro and micro structure, and that will give you these different scales. This is what we talk about. So, this is Reynolds number 1, this image, and this is 2 times of that Reynolds number. So, scale similarity says that for both this Reynolds number, the large scale structure or the macro structure are of similar in nature, but at the higher Reynolds number, this case, you can see the small structure that would have having a larger range. So, it increase in scale of microstructure. So, one hand you can think about the scale similarity where the large scale structure of the similar order, that is this what you can see, the that is the scale similarity which talks the large scale structure, but when you increase the Reynolds number, then your range of microstructure increases. Now, that is where the concept of energy cascade comes into the picture, and this is proposed by famous scientist Richardson in 1922. So, what it talks that the turbulent flows is composed of lot of eddies of different size. So, we can represent a eddy like that, which is order of L. This is the size of the eddy, that could be smaller one. So, we can have length scale, that is L, then velocity scale, which is UL, we can have time scale, that is tau L, which is L by UL, and Reynolds number, which is UL L by nu. So, now what it says that turbulence kinetic energy produced at large scale or macrostructure level. So, the energy production is essentially takes place. So, what it does, it means you have large RE. So, that means unstable eddies which will break up into smaller eddies, that is what is called cascade. Now, turbulent kinetic energy dissipated at small scales. So, at the scales of microstructure level. So, macrostructure contribute to the production of the kinetic energy, and microstructure level the dissipation takes place. So, here small RE, stable eddies. So, essentially if you look at the Burger equation or recall from the Burger equation, so energy transfer rate is determined by macrostructure. That means there are three different things which happens here. One is the energy production at the large scale structure, then energy dissipation at the small scale structure, and then energy transfer rate by the macrostructure. So, if you look at the energy cascade, this is what you can see, where this is the large scale structure, these are the macro structure, and these are the microstructure. So, when you increase the Reynolds number, the range of scales, that is the microstructure level, that increases. So, this is how energy transfer actually takes place. You have large structure which produce the energy, and then from there it actually goes to the second level of, it breaks down into the smaller eddies, smaller to smaller, and finally much more smaller eddies, and then finally through the dissipation, viscous dissipation, the energy transfer takes place. So, this is what the very common and well known concept of energy cascade. That means large scale structure to small scale structure, it transfer the energy, and at the smallest level through viscous dissipation or heat dissipation, these things dissipates. So, this is a very well known quotation one by Richardson. What it says that we realize that big whales have little whales that feed on their velocity, and little whales have lesser whales, and so on to viscosity. And this is a famous picture by Leonardo da Vinci, which says that observe the motion of the surface of the water, which resembles that of hair, which has two motion, of which one is caused by the width of the hair, the other by the direction of the curls. Thus, the water has eddying motion, one part of which is due to principal current, the other to random and reverse motion. Now, we can come to the primary mechanism of energy cascade, which is due to essentially vortex stretching. Now, what we can, how we can say that this is an closed vortex tube. You think about this is an eddy, and there is a small eddy labeled 1. So, it is stretched by the large eddy, and then it becomes like this. So, total velocity is given by u1 and u2, and the total kinetic energy is given by U1 square and U2 square. So, this is the amount of energy small eddy gains the energy and large eddy loses the energy. So, that means whatever energy is lost by the large eddies, it is gained by the smaller eddy. So, primarily mechanism that works behind the energy cascade is the vortex stretching mechanism. So, you have a eddies due to the small level of eddies, due to the large level of eddies it gets stretched like this, and then the energy keeps on transferring from one to another. Now, you can think about eddies like an vortex teeth. So, which are many parallel vortex tube. So, flow is invisibly unstable because of the KH instability. So, these vortex sheets actually, so there is a gradient between the upper and lower surface. So, they roll up. So, that is your KH kind of instability. So, that rolls up. Now, this rolls up of the vortex teeth generates new vortex teeths and process repeats itself. So, which will lead to generation of smaller and smaller scales. That means, through the stretching mechanism or vortex teeth mechanism, that smaller and smaller scale structures are keep always formed. So, now we can scale this macro structure and also find out the energy transfer rate. Okay. So, typical scales of macro structure is order of L and the velocity is U L naught, which is capital U. Now, energy of large eddies, so they will be order of U naught square. Then one can find out the lifetime of large eddies, which is order of L naught by U naught. So, my energy transfer rate is U naught cube by L naught. So, essentially that is my viscous dissipation rate at small scale is energy transfer rate at large scale. So, my epsilon is order of U cube by L naught. So, it has been shown both experimentally and through modeling also that epsilon typically found to be order of half of U naught square by, this is observed experimentally and modeling, that this is the order of dissipation. So, that which important information here is that the viscous dissipation rate at the small scale is of the order of the energy transfer rate at the large scale. Now, we can scale the, or we can find out the scaling of microstructure or small eddies. Now, essentially the dynamics of the smallest scales or the small scale, these are dominated by viscous dissipation. So, once it is dominated by viscous dissipation, that means the parameter like nu, epsilon, these are going to play a critical role. So, the smallest scales are the Kolmogorov Gaurav scales, and that is given by 1 by 4 u eta is epsilon nu by 1 by 4 and tau eta is mu by epsilon to the power half, where Re here is defined as eta u eta by nu, which is 1. That is a low Re consistent with dominance of viscous dissipation. Now, we can find out this ratio of the Kolmogorov scale to the macrostructure, and that ratio one can find out eta by L naught is order of Re naught minus 3 by 4 u eta by u naught Re naught 1 by 4 and tau eta by tau naught is to the power minus half. So, that is where Re naught is u naught L naught by nu. Let us say for example, if this is 10 to the power 5, my eta by L naught would be 1 by 6 into 10 to the power 3. So, that is the scaling. So, this is an connection between my macro structure with the Kolmogorov length scale. So, at the large scale structure and the small scale structure, the scaling parameters are different. Now, if we put that energy cascading concept in a platform, this is my dissipation. So, this is the production of the energy at the macrostructure level or the large scale structure level. So, this is my length scale, and this we call it a energy containing range, or this is the my macrostructure level. From here the energy gets transferred to the small scale, and this is my transfer of the energy, and this going towards from the macrostructure to the microstructure level or universal structures smaller scale level, and this range is inertial range, and when it goes to the smallest scale, it actually dissipates through the viscous dissipation or heat. So, this range is called the dissipation range. So, there are three range one can think about in this spectrum. There is a energy containing range. So, if I put that in a qualitatively, this is energy, there is a energy containing range, there is a inertial range, and there is a dissipation range. So, this is how the demarcation would be. This is LEI, this is LDI. This is my inertial range or a energy containing range, this is inertial range, and that is the dissipation range. So, there is a production, there is the energy transfer to the smallest scales and the amount of energy through viscous dissipation. So, the total energy balancing is also there. Now, we can at the different range we can look at the scaling of these eddies. So, first we look at the inertial sub range. So, what we look at it, that the size of eddies in the inertial sub range is in between, it is larger than eta, but it is smaller than L naught. So, here the characteristics parameter would be epsilon and eddy size. So, the scales are of L, velocity scale would be epsilon L to the power 1 by 3, and time scale would be L square by epsilon to the power 1 by 3. Now, if I relate with the relation with eta and macro scales, what I get, u eta L by eta to the power 1/3 equals to u L, which is order of u naught L by L naught 1 by 3, and tau eta into L by eta 2/3 equals to tau L, which is order of tau naught 2 by 3. So, this is for u eta less than u L u naught and tau eta is lower than tau L and tau naught. So, that is how you get the different sub range scales in the inertial sub range. So, that brings to an important Kolmogorov hypothesis. These are very important three hypotheses which proposed by the. Now, this is for high Reynolds number, that means the things are in turbulent in nature. So, there is first one is the local isotropy of the microstructure. That means anisotropy of the macrostructure is lost during breakup of large eddies into smaller eddies. So, these are the large eddies which breaks into the smaller eddies. So, there is a anisotropy of the microstructure, and that is one important hypothesis. Then the first similarity hypothesis says that the statistics of the microstructure have a universal form and the scales in the dissipation range are uniquely determined by epsilon and nu, which are known as Kolmogorov scales. And I have seen how epsilon and nu they are connected with the scaling parameters. Second similarity hypothesis, which says that the scales in the inertial subrange are uniquely determined by epsilon and the large eddy size L. So, that is what the Kolmogorov's hypothesis are, and it talks about local isotropy of the microstructure, first similarity hypothesis and the second similarity hypothesis. So, that will move to now we look at the, since this flow is quite random and chaotic in nature, we will now look at the statistical description of this turbulence. So, we will look at some turbulent signal to be analyzed, then we look at the Reynolds number decomposition, then from there we will derive the Reynolds average equation and then the Reynolds stress, and then finally, the closure problem and the issues associated with. So, when you look at the statistical part of it, that is a typical example of a turbulent signal. So, it is an velocity signal which is obviously instantaneous velocity. So, it actually shows this kind of signal. This is my real time acquisition. Now, when I do some averaging of that signal, so these noises which are shown here, so they get smoothened out and I get a nice mean kind of things, and from my instantaneous signal to this mean, if I subtract, I get this noise back. So, essentially this guy and this guy in combinedly giving me back the original signal. So, original signal has some mean of this signal, and then top of that there is the noise which is sitting there. Now, one can find out this running average over a time like the instantaneous signal and got the with the integration of that. So, that means my instantaneous signal is sum of some mu, a mean signal and plus some fluctuating component. So, that is what it does. Now, when you do this averaging, so the immediate questions which may arise, that how long one has to do this averaging or how large it could be. So, this is my instantaneous signal which is noisy in nature, and this is my mean, and this is my instantaneous. Now, depending on the t, this mean could be different. So, if t is small, some fluctuations maintained in the averaging, and if t is too large, then this could be, the noise could be smoothened out. So, average out all the turbulent fluctuations when t is actually theoretically goes to infinity, which is essentially a desired phenomena. That means, if I want to get that mean data then theoretically I should have this averaging for a sufficiently large amount of time, which is practically again impossible. So, if the T much larger than the time scale of the largest time scale of the turbulence, which is order of integral time scale of macrostructure. So, whether it is a measurements or simulation time, this becomes sufficiently large. So, now we have different kind of averaging technique. One is the time averaging. Okay. So, this time averaging, this is quite suitable for measurements at a fixed point, and this has problem when the mean is also varying. That means, if you have a time varying mean, then there is a problem. So, which clearly an issue if you have a statistically unsteady turbulence, that means atmospheric boundary layer, day or night cycle, seasonal cycle. So, that kind of situation, this time averaging won't work. Now, one can do line averaging. So, which is, so this is an averaging along a line, and I can get or express this like minus L by 2 to L by 2 u x plus tau d tau. So, that is what the line averaging does. Then finally, you get ensemble average. So, this is something like you can repeat the experiments. If you are doing experiment, repeat the experiment multiple time and average out all over the experiments, or in simulations also you can take the averaging for multiple times, and so this is what allows you to do turbulence realizations. So, ensemble averaging you can represent like u bar n equals to 1 by n summation alpha equals to 1 to n, where x t alpha. So, that is what you get in ensemble averaging, and n is the that number of repetitions. Now, here important point to be noted here is that turbulent fluctuation from different experiments are uncorrelated. So, this is an important point to be noted. So, that means one can do averaging in three different ways. One is time averaging, so which is quite suitable for measurement at a fixed point, but this is not suitable if you have statistically unsteady turbulence, like where the mean flow itself is varying. So, there it does not, like atmospheric boundary layer when it goes day or night cycle. Then one can do line averaging, which is averaging is done along a line like this, or one can do ensemble averaging, where actually you can repeat the experiment multiple times and get the, but this is where the turbulent fluctuation from different experiments are uncorrelated. So, this is how you get the averaging, and we stop here today and continue the discussion in the next lecture.